When we graphed linear functions, we often used the integers from -2 to 2 as our input values, and we called these the 5 key values. As we move into graphing absolute value functions, we're going to follow a similar concept. However, since the absolute value function is a bit more complicated than linear functions, we're going to use the integers from -3 to 3 instead. And we're going to call these numbers the 7 key values. So, let's graph the absolute value parent function, starting by finding the output for each of our inputs. Then, when we graph the resulting points, we can see that they fall in a V shape. And if we were to keep graphing points, they would all fall along this V shape, resulting in this graph. As we graph other absolute value functions, we'll see that they all have this basic shape. So let's jump into it and graph some more absolute value functions. For our next function, let's consider f of x equals the absolute value of x minus 4. We'll once again use the 7 key values as our inputs, and this time, we'll also make an extended table of values to show the steps of the evaluation process. Then, we're ready to graph our points. As we plot each point from our table, we start to see the shape of the graph. And as we finish plotting, we can see that all of these points fall in a straight line. But hold on, isn't the graph of an absolute value function supposed to be a V shape? It sure is. But unfortunately, the inputs that we chose didn't show us enough of the graph to see where the V shape occurs. So let's extend our table of values and continue plugging in new inputs. When we plug in 4 and plot the corresponding point, it still falls in the same straight line. So let's plug in 5 and plot that point. And there we have it, the first point that breaks the linear pattern. And just to make sure that the new upward trajectory continues, let's plot 2 additional points, which will show us that the function does indeed continue on its new trajectory. Now, even though we successfully completed this graph, it was a bit annoying that we had to find and plot 11 different points to do so. So let's consider which points on this graph were the most important for us to plot. The bottom point, where the graph changes directions, formerly known as the vertex, is the principal point to know about. And if we then plotted 3 points on either side of the vertex, that would make these 7 points the most important. So let's take a look at these 7 points in our table of values, because there's something special about them. Notice that these points correspond with our 7 key values. The correspondence is just in a different column than what we may have initially suspected. So why did the 7 key values show up here? Well, it turns out that we want the 7 key values to show up in our table just before we take the absolute value. And since the first step of our function was to subtract 4, that meant that we had to move our inputs higher up on the number line so that when we subtracted 4, we got the 7 key values. Therefore, the most meaningful inputs for this function were the integers from 1 to 7. To continue building on this idea of meaningful inputs, let's take a look at 2 more functions. First, consider g of x equals the absolute value of x minus 4. While this function may seem very similar to the last function we considered, notice that the absolute value bars are only around the x this time. This will have a significant impact on the inputs we choose because the absolute value is the first step occurring in this function. And since we want our 7 key values to show up just before we take the absolute value, that means that we can use our 7 key values as our inputs this time. Then, as we fill out our table and plot our points, we can see that we get the nice V shape with 3 points on either side of the vertex, which is exactly what we wanted. Then, for our last function of this section, let's take a look at h of x equals the absolute value of x plus 2 plus 3. This time, the absolute value is not the first step occurring in the function. So let's build our extended table of values and locate the column where the absolute value is occurring. Then, we want to place our 7 key values in the column just before we take the absolute value, which is here. This means that we have to work our way backwards to figure out what numbers belong in the first column. Since we're adding 2 as we go from the first column to the second column, if we want to go the other way, we can simply subtract 2 from the values in the second column to get the values that belong in the first column. Once we do this, we can complete the rest of the table, plot our points, and finish our graph. You may have noticed in the last section that there was a relationship between the numbers in a function and the location of that function on the graph. In this section, we'll explore that relationship further to help build our understanding of absolute value graphs. Let's kick things off with the following function. However, instead of immediately graphing this function, let's take a step back and graph the parent function as f. As we do this, we're going to use a different color in association with each of our key values. Once we have this graph complete, we can go ahead and make our extended table of values for g of x and plot those points as well. Once again, keeping the same colors associated with each key value. This coloring strategy will allow us to clearly see how certain points moved as we went from the parent function to the child function. And if we draw arrows to represent that movement, we can see that each point from the parent function moved 5 units to the left. Now this may seem a bit counterintuitive that the child function moved left, even though the operation inside the absolute value bars was addition. We might have thought that adding 5 would cause the parent graph to move 5 units to the right. But to understand why it moved left instead, we need to look at our key values for g of x. Since the key values needed to be placed in the second column after we had added 5, that meant that we needed to subtract 5 from our key values to get our input values. This inverse effect resulted in the leftward movement. For our next function, let's consider this one. Once again, we're actually going to start with the parent function, but once we have that color-coded and graphed, we can move on to our extended table of values for the child function. Recall from earlier that since the absolute value is the first step happening in this function, we can conveniently use our 7 key values as our inputs. Then, as we finish off our table and graph our points, we can see that each point in the child function is 8 units lower on the graph than the corresponding point from the parent function. Now it's time for a bit of analysis of the last 2 graphs that we've looked at. In both instances, our graphs changed locations relative to the parent function by shifting or sliding in a certain direction. This shifting or sliding is referred to as a translation. So both of these functions were examples of translations. Additionally, one of these functions moved left while the other moved down. Movement to the left or to the right is called horizontal movement, so the first graph was an example of a horizontal translation. In a similar vein, movement up or down is called vertical movement, so the second graph was an example of a vertical translation. Then, we should ask ourselves, why was one of these a horizontal translation while the other was a vertical translation? Well, the answer may already be apparent to some of you, but it has to do with the location of the numbers in the function. Notice that the plus 5 was inside the absolute value bars, whereas the minus 8 occurred outside the bars. When we add or subtract outside the absolute value bars, it results in a vertical translation. But when we add or subtract before taking the absolute value, it results in a horizontal translation. With that, let's do a bit more practice and consider one final function for this section. This time, the function has subtraction inside the absolute value bars and addition outside the absolute value bars. So based on the translations we've previously analyzed, we can make predictions about the final position of this function. First, the subtraction inside the absolute value bars should move the parent function 3 units to the right. So let's draw the parent function and an additional function shifted 3 units right. Then, the addition outside the absolute value bars should move the function 7 units up, which gives us this graph as a result. Now that we have a prediction of our final graph, let's make our extended table of values for the function and see what we get as a result. And there we have it. The points in our table of values match the points from our prediction, so our prediction was correct. During this video, we regularly mentioned and used the 7 key values. And as we consider different types of function transformations, and even different functions, this concept of key values will continue to pop up. So, to conclude this video, let's spend a little time formalizing some of the language around key values, along with the corresponding concepts of key inputs and key points. First off, key values are numbers that we can plug into a parent function to get a well-rounded picture of what that parent function does to a number. In this video, we considered the absolute value parent function, and our key values were the integers from -3 to 3. And these 7 integers will also serve as key values for several other functions, so we'll regularly refer to them as the 7 key values. However, we will eventually encounter functions where these 7 key values don't give us a good picture of the function. So in these instances, we might adjust the 7 key values to be different numbers, or we might only have 5 key values, or we could end up with more than 7 key values if necessary. Either way, the key values for any particular type of function will generally stay consistent. Additionally, recall from earlier in this video that the 7 key values didn't always appear in the first column of our table of values. Instead, they showed up right before we took the absolute value. When we find ourselves in a situation where the key values are not our inputs, it's still going to be useful to have a way to refer to the inputs that lead us to our key values. And we'll call these inputs the key inputs. For example, in this function, we need to subtract 6 from our 7 key values to achieve the inputs of the function. Thus, these 7 numbers would be our 7 key inputs. In general, the key inputs are the numbers that we will plug into a function so that we achieve our key values right before we apply the parent function. In some instances, these key inputs might be exactly the same as the key values, but in many other instances, they'll differ based on the numbers in the function. And once again, we might not always have 7 key inputs, but the number of key inputs will always correspond with the number of key values. Finally, we have the key points, which are the input-output pairs that we get when we plug the key inputs into our function. Graphing these points should give us a fairly complete picture of what the function will look like, and will allow us to draw the final line or curve that represents the function. Thus, for our example on the screen, these would be the 7 key points. That concludes this video on graphing absolute value functions with translations. Hope you learned something new, and thanks for watching.